Welcome back, everyone, to today's Masterclass Explainer. So let's jump right in because we need to clear up a massive misconception in software engineering. There's this idea that once you finally deploy a program, once you hit that big button and go live, you've crossed the finish line. Well, I'm here to tell you that going live is absolutely not the end. In reality, it's just the very beginning. The messy, complicated, real-world reality of business and politics is where our carefully crafted software actually has to survive. And honestly, understanding that reality is exactly what separates good coders from truly great systems engineers. Looking at our syllabus for today, we're going to cover quite a bit of ground. We'll start with an introduction to system operation, talk about the crucial human element, and then dive into system evolution. After that, we'll figure out exactly why obsolete systems survive for so long, look at the inherent dangers of that evolution, and wrap up with a high-energy Chapter 19 master recap to get you completely prepped for your exams. All right, let's kick things off with Section 1. What happens when our system finally meets the real world? So, think about what actually happens on day one of a new system being brought into use. The operational processes you planned for almost always have to change to reflect the real working environment. The way you brilliantly designed the system to be used is, quite frankly, rarely how it's actually used by real people. This brings us to an incredibly important concept called domestication. This was referenced by Stewart and Williams back in 2005. Basically, domestication is that critical period right after deployment when users adapt to a new system and work out the practical processes of how to actually use it. You see, your user interface might be logically perfect, but human users are the ones who establish the actual behavior of the system by figuring out practical workarounds. They find the absolute quickest way to get their daily jobs done, which means they effectively domesticate the software into their own routines. So, just to recap this point, your operational plans will always change in the real world, and domestication is that crucial, unavoidable adaptation phase. Moving on to Section 2, let's talk about the human element, and specifically why we absolutely do not want to automate everything. We've all heard this pervasive myth, right? The idea that systems should be fully automated to completely minimize human error. Just remove the user entirely. But here's the catch. Fully automated systems are incredibly brittle. Trying to build a system that can handle every single anticipated failure mode is just exponentially expensive and practically impossible. Now, compare that to human operators. Humans are amazingly adaptable. When some totally unexpected failure occurs, it's actually the human operators who step in and save the day. They use their local real-world knowledge to find quick workarounds and keep things running. This brings us to a fantastic quote from the text that sums this up perfectly. People have a unique capability of being able to respond effectively to the unexpected, even when they have never had direct experience. Seriously, underline this in your notes for the exam. Human operators are a massive benefit because they don't just freeze and crash when something unprogrammed happens. They adapt, they improve processes on the fly, and they keep the entire socio-technical system running when the code alone just cannot. So humans aren't the problem. They're the ultimate backup plan. All right, Section 3. We're zooming out now to look at system evolution over the long haul. We're shifting our focus from those day-to-day operations to the macroeconomic and technical realities of long-term system survival. First, let's get our definition straight. System evolution is the ongoing process of changing and extending a system's hardware, software, and operational processes over its entire lifetime. We're not talking about a little mobile app that gets replaced in a year. Large, complex enterprise systems often survive for 20 or more years. This means evolution is running continuously alongside normal, everyday operations. You are constantly in there correcting errors, adapting to new hardware requirements, and responding to a wildly changing business environment. So, system evolution isn't a one-off event. It's a continuous, decades-long process of survival. Which leads us perfectly into Section 4. Why exactly do these systems live for so incredibly long? Okay, think about this paradox for a second. If a system is 20 years old, the technology running it is completely, hopelessly obsolete. So why on earth do businesses continue to rely on them? Well, there are 5 critical factors we need to look at here. First up is investment cost. These monolithic systems cost tens of millions of dollars to build. Businesses naturally demand a very long lifespan to justify that initial price tag. Second, and this is fascinating, is the loss of expertise. Over the decades, the original developers who knew how the system actually worked end up leaving or retiring. This means the organization literally loses the internal ability to even specify the requirements for a replacement. Third, the sheer replacement cost is staggeringly high.
Fourth is return on investment. Sometimes a company's IT budget will simply yield a much better ROI if they spend it on a flashy new customer app rather than ripping out and replacing a backend that technically still works. And finally, we have the risks of change.
Let's really expand on that last factor, the risks of change, because it is an absolute deal breaker for most companies. When you try to rip out a core legacy system, you open yourself up to massive hardware, software, and operational failures. Imagine a major national bank deciding to replace its core transaction program over a weekend. If that replacement fails and causes a critical business interruption, the bank suddenly can't process payments. Millions of customers are locked out. A failure of that magnitude could literally bankrupt the entire institution overnight. That sheer, terrifying risk alone is enough to keep old systems alive for decades. So they evolve continuously, and they survive, simply because the cost and risk of replacement are just too high to stomach. Okay, on to Section 5. We know why they stick around, but let's talk about the dangers of this evolution, or what we call the legacy trap. Keeping these ancient systems on life support brings some massive headaches. First, we need to clearly define a legacy system. These are socio-technical, computer-based systems developed using obsolete technology, and they are heavily reliant on legacy processes and procedures. Now, I want you to pay very close attention to that last part. A legacy system isn't just a bunch of old code sitting on a dusty mainframe in a basement. It heavily includes entrenched, old ways of doing things. It's the human processes and organizational habits that have hardened over decades, and those are incredibly difficult to change. Evolving these legacy systems is inherently costly and, frankly, quite dangerous for 4 key reasons. Number 1, any proposed changes require heavy, expensive business and technical analysis just to figure out what might happen. 2, because all the subsystems are tangled together over the years, changing one tiny thing over here causes completely unpredictable side effects somewhere else. 3, the original design decisions are almost always unrecorded and completely lost to time. And 4, honestly, this is the scariest one for any engineer. New developers might unknowingly break or remove an undocumented safeguard. You know, they go in to change a variable to improve processing speed, and suddenly they've completely removed a vital security check that no one wrote down 20 years ago. Because of this, over years and years of ad hoc patches, emergency weekend fixes, and quick workarounds, the system's underlying structure becomes heavily corrupted. This is what we call the spaghetti code trap. It's exactly what it sounds like. Every single subsequent change you make becomes exponentially more expensive, dangerous, and time-consuming because the software architecture has degraded into a tangled, fragile mess of interconnected dependencies. So, in summary, legacy systems are fundamentally trapped by unrecorded decisions and incredibly fragile patched-up architectures. All right, take a deep breath. We are moving into our final section, the Chapter 19 Master Recap. Let's do some rapid-fire exam prep. We've covered operations and we've covered evolution. Now, let's consolidate everything you need to know for that final assessment. First up, you need to clearly distinguish between these two disciplines. Software engineering is concerned primarily with the practicalities of just developing the software itself. But systems engineering is a much broader field. It's the overarching activity of designing entire systems. That means the hardware, the software, the operational processes, and the human elements. It is a complete socio-technical process. And I want you to visualize how this socio-technical reality is actually structured. The technical system, the code, and the hardware sits right in the center. But it doesn't exist in a vacuum. It is heavily surrounded and embedded by layers of organizational constraints. You've got operational processes, rigid organizational policies, company culture, and even national laws wrapping around it. As a systems engineer, you have to design for every single one of these layers, not just the code in the middle. Next vital concept you need to remember, emergent properties. These are properties that belong to the system as a whole, rather than to its individual parts. Basically, the whole is greater than the sum of its parts. These properties only become apparent once the entire system is integrated and turned on. You absolutely cannot measure an emergent property just by looking at a single line of isolated code. It only exists when the software, the hardware, and the human users all start interacting together. You also need to have the 4 phases of the systems engineering lifecycle locked in your memory. Phase 1 is conceptual design. Phase 2 is procurement. Phase 3 is development, and Phase 4 is operation. And remember, Phase 4, operation, is exactly where the domestication and system evolution we've been discussing today actually take place. Okay, listen up. Grab your pens, because this is your core exam focus. You absolutely must be able to do these 3 things. First,
Clearly define the domestication period. Second, you need to effectively argue why human operators are beneficial. Remember, humans use their local knowledge to adapt to unexpected failures, which allows us to avoid building brittle, over-automated systems. And third, memorize at least 3 of the reasons we discussed for why large systems outlive their obsolete technology. So investment cost, replacement risk, loss of expertise, those kinds of things. If you can confidently answer these 3 points, you are going to be in fantastic shape for the test.
And that brings us to the end of our explainer. A huge congratulations to all of you on completing your study of Chapter 19 and really mastering how software operates out in the wild. But before we go, I want to leave you with one final, provocative thought. As you step out of the university classroom and into your actual engineering careers, how are you going to navigate the messy, unpredictable real world of business and politics, where writing perfect code just isn't enough? Remember, hitting that button and going live is just the beginning. Thank you so much for learning with me today, and I'll catch you in the next explainer.